Okay, it's recording. Okay, welcome back. So this is the second lecture on quantum physics or quantum mechanics. And I'm going to start with reviewing what we discussed last time. And then I'm going to spend some time to play around with the equations, to solve some examples, just to see how this works. So basically what we discussed last time was Max Planck idea that once you have a light in thermal equilibrium, then light can be emitted or absorbed by these small portions. And if you look at the constant, which is called Planck constant, the portion is really, really small. So this is 10 to minus 34 joules multiplied by second. It's one of the fundamental constants which we call the Planck constants. Yeah? So feel free to stop me anytime and ask questions. And maybe I will need some help from you when we will do calculations. The second multiplier is the frequency of light. And typical frequency of light is, of visible light, let's say, 10 to power 14, 10 to power 15 hertz. And even if you have 10 to power 14 for frequency, you can see that this 10 to minus 34 will make this energy portion extremely small. So if you accept this idea of Max Planck, that light is emitted by small portions, then you can use statistical physics and calculate the average number of these portions at given temperature. So and this is called Planck distribution, or you can just refer to this as a number of photons or number of portions at given temperature. So and I want to just to show one more time what is inside this HF over KT. This is what I put inside the index. H is the Planck constant, F is the frequency. Basically, this is the energy or at this frequency of the portion. K is a fundamental constant, it's called Boltzmann constant. It's pretty small. And T is the temperature in Kelvin. So, and last time I tried to convince you that if you accept this Planck idea that there is a minimum possible energy portion for given frequency, then this idea introduces natural cutoff parameter for the maximum frequency we can have. So, and I would like to continue from this, and then we can do some examples about it. So, if you look at energy associated with certain frequency, then you just take energy of one portion, and then I would start to call this photons, yeah, multiplied by average number of photons. So then we can say HF over exponent HF over KT minus 1. So let's play around a little bit with this average energy for given frequency. How can we see that this cutoff parameter appears? First of all, if you have exponent at x, and x is very small, do you know what is the asymptotic behavior for the exponent when index is very, very small? Some of you?
Equal 1? Or?
Yeah, exactly. It will be 1. What will be the next correction to this 1? This is called Taylor expansion. So the next correction will be just x. If you want more corrections, that's going to be x squared over 2 factorial and so on. But I will just restrict myself by first 2 terms. So I can look at this expression when the index of the exponent is very small. So then I say if HF over KT goes to 0. Probably I can say my temperature is very large. or my frequency is low. So I have different ways how I can make this ratio small enough. In this case, can you help me? What's going to be the energy for given frequency?
Because mine is HA. Or no.
HF, it's a numerator, yes?
Yeah.
The exponent, because my index is very small, can I replace it with 1 plus x?
Yes.
So I'm going to say 1 plus
6.
HF over KT. This is my x, the index. And then I have to subtract 1, this one. Apparently, I cannot say that this is equal because I neglected other terms. But I can say approximate, yeah? At a very high temperature or at low frequencies, this would be the average energy in one frequency. And then I can simplify it, yes? Can I cancel 1?
Yes.
And what will be the result?
KT.
KT, yeah, thank you. KT. So this result will stay for a long time, for long frequency, until you keep this parameter small. So the conclusion for this, if my HF less than KT, then the ratio is small, then the average energy for given frequency as a function of frequency would be proportional KT. And this is very good because it makes sense. This is what I tried to explain last time. If you try to plot this average energy for given frequency, for different frequencies, my expectation should be KT. But we had a problem. We call this ultraviolet catastrophe because we did not know how to cut it. This is supposed to go to very large frequencies. And if you cannot stop, then the integration over all frequencies will give you infinity. So you have a problem at higher frequency. But at low frequency, this Planck distribution gives you a reasonable result. Something what you expect at low temperatures. Okay, that's fine. What will happen to this distribution if I consider high frequency? So the second asymptotic behavior. What if my parameter HF over KT is very large? So basically it goes to infinity. You can look at this as frequency goes to infinity, or you can say the temperature is very small. Then what can we say about the exponent? The index now is very, very large. What can you say about the exponent?
Goes to infinity?
Yeah, it will be very, very large, yes? Even larger than the parameter itself because it's exponent. Then, if I look at my distribution, can I neglect this one compared to very, very large exponent?
Yes.
Yes.
Yes, and then I can say, again, approximately, in this limit, the average energy for given frequency will behave like HF multiplied by some exponent minus HF over KT. So, and I put negative exponent because I have a big exponent in denominator, yeah? I can move it to numerator, but I have to put the negative sign. This is very interesting because at higher frequency, I have exponential decay or exponential decrease of this average energy. And then when you have intermediate frequency, then you have some smooth behavior between low frequency and high frequency. And you have this threshold, F typical or F max or F critical. And this is basically the typical frequency where you have a decrease in average energy. And this will be dictated by the exponent. When the exponent will be large enough, then I'll start to feel that my distribution is going down. So, and I can say HF max, but max may be not the best wording here. It's like a typical or critical. So the index of the exponent should be order of 1. If this index is very large, I have exponentially small energy. If this index is very small, I have KT. And when it's order of 1, then I have something intermediate. It will give me the typical frequency from this. KT over H. And this is sometimes people call this Wien's law or Wien's displacement law. That this typical or maximum or peak frequency is actually proportional to the temperature. So in this case, the area under the graph would be finite. And if I integrate over all the frequencies, so the total energy would be finite, so I can solve the ultraviolet catastrophe. This kind of repetition from what we did last time, maybe in a little bit more details when we look into this Max Planck distribution. Yeah? Do you have questions? So you're still with me, yeah?
Yes.
Yes.
Okay. So it explains why we have finite total energy in black body radiation. And I want to spend a little bit of time to show you that the total energy is proportional to temperature power 4. This is what's called Stefan Bosman Law. Yeah. Then how can we get the total energy? Basically, total energy would be summation over all possible frequencies from what we just discussed. So if you have energy for one frequency, but what if you have many other frequencies? You have to do summation. This summation would be the energy you have this is a Planck distribution for the average energy multiplied by something which last time I tried to give you a hint that it's better to use a wave vector delta 3k, the volume, and over 2 pi cube. If I want to be very accurate, I would put extra factor 2 here because of the polarization. Because light can have different polarization, and so you can fit more light, more energy for given frequency. So some of you may know that particles have spin. And this corresponds to spin of photon, this factor. So just a very quick, if you have a photon, then the spin can be a long motion or spin can be opposite to motion. So you have two different components of the spin. Even so, the spin is 1, not 1/2. But probably for most of you, it doesn't say much. So then we can talk about polarization of electromagnetic radiation. Then the electric field can be polarized in different directions. So, and you can split it into two. But because we want to just have a proportionality, because we just discuss it basically qualitatively, I just put proportionality. And if you want, you can keep factor 2. If you don't want, just forget about it. So my goal would be to show you very brief how you can get temperature power 4. Because this guy, the average energy, it's no greater than K, than temperature, KT. Yeah? Maximum what you can have is KT. And then if you reach certain frequency, you go down. How can you get temperature power 4? Because of this integration. This integration, if I integrate over volume, okay, I don't want to integrate over volume, I want to divide by volume. But the integration over K vector can be related to omega. How can we relate the wave vector and angular frequency? Some of you should know. The hint would be with the speed of wave. The wave vector and omega related by the speed of wave.
Lambda O.
Omega over c or omega multiplied by c, or how?
Omega over C?
Omega over c, yeah? The omega is 2 pi f. So basically when we're talking about integration in K space, it's restricted by frequency. And then frequency is restricted by f max. Yeah? After f max, this denominator becomes very large, exponentially large, and your energy goes down exponentially, and you can stop integration. Would it be obvious for you if I tell you that when you integrate over d3k, you're gonna get something like a volume in this K space, like 4 pi over 3 K max cube. How obvious is this? It's basically a sphere, the volume of a sphere of this radius. Can you recognize it?
Yes.
4 pi r cube over 3. But because my integration in wave vector space, then I have to put a maximum k. But my maximum k would be restricted by frequency, yes? I'm gonna write proportionality because right now I'm trying to do estimation. So 4 pi over 3, k max is gonna be 2 pi f max over speed of light cube. And this is pretty natural, that the volume of integration for K space is restricted. Inside this volume, your average energy is roughly KT. Outside of this volume, your energy is roughly 0. But what is F max? How big is this K max? How big is F max? Can we look at this Wien's law? The F max is proportional to temperature, yes?
Yes.
If I have greater temperature, then F max will shift towards higher frequencies. So then if I try to write proportionality, I would say I have kT over h by h over speed of light cube for the volume. Did I forget to put something? kth, speed of light. Okay, pi's. Okay, let's collect all the pi's. Pi cube, pi power 4. And maybe some constants like 4 over 3 and 8. So now I can plug this for the integration over d3k. And I'm gonna get the total energy would be proportional the typical energy of light of given frequency, which is kT, multiplied by volume, it's normal volume in space, and also multiplied by volume in k vector space, which is kT over hc cube. And the miracle of this, that suddenly I'm gonna get temperature power 4. Okay, I don't need other constants. But can you see that this is temperature power 4? Temperature was initially from the energy, and then temperature power 3 came from the integration over k. How do you like it? That was experimental fact. And with this distribution, we can explain this experimental fact. And the constant of proportionality will depend on fundamental constants. It's going to depend on the K constant, which is Boltzmann constant, the Planck constant, and the speed of light. If I look back what we discussed last time, probably that is a maximum what I want to repeat from last class. Because last time I didn't show you how temperature power 4 can be explained. So now you can see this. So if you like it, then I can just solve a couple of problems for you so you can see how it actually works. So let's formulate what's called Stefan Boltzmann Law. And let me know if you have questions. So the Stefan Boltzmann Law, we can formulate it many different ways. One way we can say the energy total over volume, this would be density of energy, is proportional to temperature power 4 with some coefficient. This is a density of energy of black body radiation. Another way to formulate Stefan Boltzmann law to consider intensity. Intensity means you have energy per unit of area per unit of time. So if you have surface at given temperature, it's going to radiate this energy per second. It's also proportional temperature power 4 because my energy is proportional temperature power 4. Or we can speak about power emitted from the surface. Energy over temperature over time, power, it's also proportional temperature power 4. So all of this you can call Stefan Boltzmann law. So more accurately, I can say that this intensity is some constant sigma multiplied by temperature power 4. And the sigma is, if I remember this correct, 5.67 10 to negative 8. It should give you the intensity in watt per meter square, and it should cancel temperature power 4. Kelvin power 4. Again, It can help you to calculate how much energy will be radiated from unit of area per unit of time. It can help you to find the power of radiation, because the difference between intensity and power is just area. Finally, I can relate the density of energy and intensity. I would say intensity would be equal to density multiplied by 1/4 and speed of light. But we don't really have to do this. We have enough to practice with the Stefan Boltzmann Law. I would say the first one is probably most canonical, but you can use any three of these quantities. The main part of this, of course, the proportionality of temperature power 4. So you can find density of black body radiation, density of energy, or power emitted from surface, or intensity, basically very, very close to this. So let's do examples, if you don't mind, yeah? Because my goal for today, at least for half of the class, to try to go through a few examples. Example A. So if you have energy, gamma equal HF, can you find energy for certain light? Find energy of photons for wavelengths, let's say 400 nanometers. This would be something close to blue light. It's a low, short wavelengths, high frequency. So maybe it's violet or ultraviolet in the sky. It's more like violet wavelengths. What would be the energy which corresponds to these wavelengths? So this is where I probably will need your help. What would be your suggestion? How should we proceed?
HC over lambda.
HC over lambda. Beautiful, Rebecca. So we can do like this, yes? We can divide it by speed of light and multiply it by speed of light. Speed of light over frequency. What is this?
Lambda.
Lambda, the wavelengths. So I don't have to really calculate the frequency. I can just express my energy through lambda. Does it make sense to everyone, this transition? Peter?
Yes.
Okay, cool. Is Peter here? He's very silent.
Can you hear me?
No, yeah, I can hear you.
Clearly, I have two microphones. I don't know which one is connected.
Okay.
It's clear, right?
Yeah, now it's perfect.
Okay, good.
So let's calculate this constant. If you have calculators, so help me. So h is a Planck constant, c is the speed of light, 6.63 10 to minus 34 joules per second. I'm going to multiply it by 3 10 to power 8 meter per second. So if you let me, I can cancel seconds. Yep. Then power of 10, 10 to minus 34, 10 to power 8. I'm going to get negative 26 joules and meters. Can
I
you
got 1.2 times negative 25, 10 to the, yeah, 25.
can you give me more digits after 2?
Okay, 1.989. Yeah,
1.989,
89, yes,
10 to minus 25.
yes.
I like it. So it's very close to 2. Now, I would like energy in electron volts, not in joules. So 1 joule equals how many electron volts? It's going to be 1 over, I guess, yeah? Electron volts. Can we change it to electron volts? The energy, the joules. So if you can help me and divide by 1.6 10 to minus 19. 10 to negative 25 and 10 to negative 19 should give me 10 to negative 6, yeah? Minus 25.
Yes, I got 1.243.
1.243.
125. Yeah, times 10 negative 6.
Electron volts
Yes,
multiplied
times
by meter.
Yes.
I would say more accurate, if I use more digit, we should get 0 here. But I could be wrong on this. My recollection, the best what I can remember is the digit 3, the 0. But it's very hard to keep all 4 digits. That means you have to be very, very accurate. So then this can be written as a 1.24 micrometers multiplied by electron volt, or we can write it as 1240 nanometers multiplied by electron volt. And honestly, this is how I remember this constant from my student years. This constant can change nanometers to electron volts, and this constant can change back electron volts to nanometers. It's a little bit more convenient than this 10 to minus 25 joules a meter. So electron volts and nanometers are more convenient. So then if we go back to the problem, the numerator is 1240 electron volts nanometers, and denominator is my wavelengths. And this is a fundamental constant. This constant is always like this, always. So then if you have blue light, which has a wavelength 400 nanometers, what will be the energy of the photon, which corresponds to these wavelengths? So now it's a piece of cake, yeah? What should I do? 1240 electron volts, nanometers. I'm going to divide by 400 nanometers. And the energy would be
3.1 electron volt.
3.1 electron volts. The units are very convenient, yeah? What if you have something like red light? Let's say 630 nanometers. So this would be wavelengths which corresponds to red light. What is the energy of one single photon for red light? Can you do this yourself? You just plug wavelengths, yeah?
So I got 1.968 electron volt.
1.968. Can I just say 2?
Yes. Yeah, very close to 2.
Everyone understands? Do you have questions about this?
No.
No, I mean you understand, or you don't, or you okay. So then from energy point of view, this is basically my visible light, yeah? From energy point of view, the energy for visible light is kind of in between 2 and 3 electron volts. If you have a shorter wavelengths, then you will get more energy, but there's going to be already UV light. For shorter wavelengths, higher energy, higher frequency, you go beyond 3 electron volt, that would be UV light. This is a very long wavelength. It corresponds to 2 electron volt. It's less energy than UV light, but what if you have longer wavelengths? The energy will be less, yeah? This would be infrared photons. If you look back through the example A, does it all make sense? Do you have questions? So far so good, yeah? Okay, example B. Let's look at hydrogen spectrum. Hydrogen spectrum. If you look at energy levels of electron, the lowest energy is negative 13.6 electron volt. This is the first level, the ground state. The next level would be 4 times less. So it's going to be minus 13.6 over 4 electron volt, because the energy in hydrogen equals to negative Rydberg constant over n square. So this is n equal to. And then the level number 3, n equal 3, would be negative 13.6 over 9, yeah? Because I want to plug n equal 3 in this equation. If you can help me briefly, what are these numbers? So I have just not fractions, but numbers for n equal 2 and n equal 3. This should be like
3.4.
3.4 electron volt.
Yeah.
And what about the n equal 3 level?
1.51. 1.51.
1.51 electron volt.
Yep.
Okay, these are the energy levels of electron in a hydrogen atom. Let's say you have an electron which is in excited state, like for example n equal 2. When electron jump down to n equal 1, it will emit light. The energy of this light would be the difference between energy levels of the electron. But once we know the energy, we can find what kind of light is emitted, what kind of frequency of this light, what kind of wavelength of this light. So let's find energy of these photons. Find E gamma for n equal 2 to n equal 1 transition, from n equal 3 to n equal 1, and from n equal 3 to n equal 2. You may have different transitions, yes, when electron jumps from second to first and from orbit number 3 either to 1 or to 2. In all these cases, what would be the difference in energies? And the difference in energies would be my energy of the photon. Okay, help me with this. You jump from second level to first level. You take
negative 10.2.
I would just say maybe positive 10.2 because this is what the electron is gonna lost, but photon is gonna gain. Let me write it. Initial energy of electron will go to final energy of electron plus photon. Then when you calculate E final minus E initial, this is what electron is losing. And of course, it's going to be negative. But for the photon, there's something you're going to gain instead. It's going to be initial minus final. So then your answer is perfect. But I would just say the photon energy should be positive. How much did you say?
10.2.
10.2, and units are
Electron
volt.
volts. Yeah.
What about 3 to 1? If you jump from 3 to 1,
I got
11
12
point, or 12.11. Yeah.
yeah, 12.09.
I'm sorry, 12.1.
09 or 1, yeah, 1, yeah. Electron volt.
These are huge energies. What about 3 to 2? Sorry for this background noise. It's ambulance.
I got 1.89.
1.89.
89. Yes.
What can you say about these two transitions, 2 to 1 and 3 to 1? The energy. Is it visible light?
It's ultraviolet.
Say it again.
It's ultraviolet.
It's ultraviolet. So this is a visible light, yes? If you have higher energy than this, it's already not visible light. It goes beyond the violet color. What can you say about this one? It's something very close to red.
Yeah.
This is very famous H alpha light. Yes, Amar?
Yeah. Yes.
In hydrogen spectrum, something close to 1.9, 1.89 yeah, electron volt. This should be your famous transition which people use in astronomy, H alpha line. This transition is a very characteristic for example, for our sun, for stars. And you can make a filter which will only let this energy, this frequency to go through. So then you can remove all other frequencies and just see this light. Okay, this is lyrics. Can we convert these energies to wavelengths? What kind of wavelengths correspond to each energy? So kind of a second part of this. Find lambda for each E gamma. So you have a lambda for n equal 2 to n equal 1. Oh, by the way, let me remind you. So the E gamma equals 1240 over lambda, yeah? So then we can just turn this around. Yeah? And I'm gonna use the same units. So this equation is extremely convenient. So I'm gonna plug 1240 electron volt nanometers, and I'm gonna divide by the energy which corresponds to n equal 2 to n equal 1. 10.2, yeah? Electron volt. So can you see that electron volt cancels out? And my answer would be in nanometers. How much? Roughly 124, yeah? Because it's 10. Slightly less.
121.56.
0.56, yeah? And the units for this 121.6 would be
Nanometer.
nanometers. Perfect, very good. So you see, it's relatively easy to convert wavelengths to energy of corresponding photon and back from energy to wavelengths. Okay, what about n equal 3 to n equal 1? What kind of wavelengths? The energy was 12 something, yeah? $12.1. Hmm. 100?
Yeah, it's 102.479.
102.479. So apparently these are very short wavelengths because visible light is in between 406 or 700, maybe 700 it is the limit. By the way, here it's kind of inconsistent. Yeah. The typical range for visible light from 400 to 700 roughly. Yeah, it's my bad. This is very short. 400 is the shortest wavelength for visible light. This is 100. Apparently, it's UV light. Finally, the very famous H alpha line. When you have a transition from 3 to 2. When you have transition from 3 to 2, you told me that this is 1.89.
I got 656.1.
656.1.
Yes. Yeah.
Amaro should know 5 digits. 656.13 or 15. Amaro, what is the accurate H alpha line position?
I think it's a 6563, right?
Oh, maybe 3. So then we are close enough to this, yeah, with our calculation. But if you want to find 4 digits, you apparently need to have more accurate the energy levels.
6563.
Yeah, no, I know, but for these calculations, we got 1. Apparently, we don't have such much accuracy to have 4 digits. Okay, that's fine, that you can just solve such type of problems relatively easy. When electron jumps from one level to another level and you know that the difference is emitted as light, you can find energy levels and then you can solve for wavelengths and frequency by using this nice equation.
Yeah, all to 1 are ultraviolet, all to 2 are visible, and any other 1 to 3 is infrared.
What do you mean 2 to 3? Electron volts?
Any jump
Oh,
up to 1 is ultraviolet. Any
yeah.
jump to 2 is visible, or any jump to the third one is infrared. It's a Lyman-Balmer Paschen series.
Yes. Because you have other levels, and the higher you go in terms of energy, they are more dense or closer to each other. So then transition becomes very small energy. The only big energy, which means ultraviolet light, can happen if you jump to n equal 1, basically, and sometimes to n equal 2. It's kind of a borderline, yes? No, n equal 2 actually is not very high energy. But if you jump to n equal 1, your energy is always great. Yep. So if you want to have something useful to take home from today's class, I would insist that this equation is fantastic. It helps you to convert photon energy to wavelengths and wavelengths to photon energy in a very convenient units, and the constant of conversion, basically hc, the Planck constant and speed of light, is pretty much straightforward. I mean, it's a nice constant, yeah? 1240. Questions? How do you like these examples? Does it make sense?
Yes.
Yes.
Okay, let's do something similar to this. Let's calculate number of photons. So let's say you have a red laser pulse of total energy, let's say 1 millijoule. So the wavelength lambda is 632 nanometers. It's a wavelength of this radiation. So you send a pulse. So this pulse has certain energy. 1 millijoule. How many photons in this pulse?
Calculate the energy of one photon and count how many need to add up to 1 millijoule.
Okay, so then energy of one single photon. What equation would you use to find energy of photon which corresponds to this wavelength?
AC over lambda.
Yeah, 1240 nanometers over the wavelength, which is 632. Okay, that was my goal, but I somehow divided by 600. How much is this?
1.96.
1.96?
Yeah, no,
Can someone confirm this?
Yes, it's 1.96.
Okay. Then what Peter said, this is you have a pulse, yes? This means you have a bunch of photons. And gamma. They're gonna move at speed of light, and each photon has energy E gamma. The total energy of the pulse is 1 millijoule. How can you find the number of photons?
divide the total energy of the pulse divided by the energy of one photon.
The total energy of the pulse over energy of one single photon.
Yeah.
There would be a problem because
The units.
the units, yeah, 1 millijoules means 10 to minus 3 joules. And the energy of the photon is 1.96 electron volts. These are different units. Joules, we like joules for our microwatt, but electron volts, these are for photons for microwatt. So we will have to change either joules to electron volt or electron volts to joules. It's up to you. I would change maybe electron volts into joules. 1 electron volt, how many joules? 1.6, yeah? So you're with me on this. So help me. 10 to negative 3, 10 to minus 19, it should be 10 to power 15. Maybe I would say 14. And 10 over 2, 5 over 1.6, roughly 3. But you probably can correct me. What is the more accurate value for number of photons which will be in such pulse?
It's 3.18
3.2, yeah?
e to the power 15.
3.2 power 15.
Oh,
Let me double check. Oh yeah, this is 16. Yep, you're right. Thank you. Can someone confirm this? So basically, we have a tiny energy of one single photon, a tiny particle, but you have a lot of them, 10 to power 15. And at these wavelengths, they're gonna form an impulse of 1 millijoule. So when we were talking about photoelectric effect, this is how light should be considered. You have a bunch of photons of certain frequency, of certain wavelengths, and they have certain energy, and then can move with the speed of light and interact with electrons from the metal plate. Okay, so we found the answer. Questions? 10 to power 15, because this is 16, yeah. So makes sense, yes? A similar problem. What if you have power of the same laser? (632 nanometer laser is 10 milliwatt. What does it mean, power, 10 milliwatt? It means that every second, you emit 10 millijoule of energy. Just to remind you. 10 millijoule every second. This amount of energy is emitted every second, and it gives you 10 milliwatt power for this laser. Then we can ask how many photons per second is emitted. How many photons per second? What will you do to solve this problem?
32 times 10 to the 15.
Wait, not that fast. What equation would you use? We are talking for number of photons per time, yeah?
Was it 1 millisecond? It was 3.2 times 10 to the 15, right?
You mean 1 millijoule?
Oh, it was millijoule. Sorry. Right.
Yeah. No, it's fine, it's fine. 1 millijoule. 1 millijoule corresponds to 3.2 10 to power 15 photons, yeah? Then, the next step,
10 millijoules,
10 millijoule,
32
32 10 to
times
power 15 photons, yeah?
photon.
And then you emit this every second, yeah? Then there should be a number of photons per second.
Yeah.
Technically, I would say it's a energy over E gamma, yeah, per second. So total energy Oh, no. What I'm trying to say, sorry. I'm trying to find an equation to use. Number of photons. It's energy over E gamma per time. The energy per time, this is my power. So if you take power, energy per time of your laser, you divide it by energy of one single photon, you're gonna get the rate at which photons are emitted. But I like Amaro's approach better.
Well, that because it's easier because the time that you gave,
You mean the
yeah,
power?
it's a simple number, right?
Yeah, there are simple numbers. So the rate at which photons are emitted from this 10 milliwatt lasers would be basically 32 10 to the power 15, yeah? Photons per second. But you can do this direct way.
Yeah.
Power over energy of one single photon. Power is energy per time, and energy over photon energy is the number of photons. So you get number of photons per time. Yeah, something like this. Or if you don't like 32, you can make it 3.2 10 to the power 16 photons per second. So then if you see a powerful laser like this on these wavelengths, you can estimate how many photons is emitted every second by this laser. So then, even if we did not do much yet, we just started to talk about photons, yeah? Basically, we are talking about one simple equation like this.
Professor?
Yeah.
Just for homework, anybody who wants to do this same calculation, I just checked in a microwave, typical microwave oven, household one, it emits it's 800 watts power, and the wavelength is 0.122 meters.
0.122
meters.
So basically it's about 12 centimeters, yes?
12 centimeters and 800 watts. How many photons does it take to heat your drink, let's say for 1 minute?
Okay, but they form standing waves, yeah? Yeah, but I can accept it, yeah.
Okay.
So they were fun problems and so it's homework from Peter. They were fun problems and we basically work with one equation. If you want, I can talk very little about Stefan Boltzmann Law. Maybe at least one example for Stefan Boltzmann Law. It's kind of a fun law to play around. We can calculate power emitted by something heated to a certain temperature. So we need to know the Stefan Boltzmann constant, the area of this object, and the temperature at the surface of this object. Or you can calculate the flux or intensity, how much energy per unit of time, per unit of area is radiated from this source. Or you can find the density of energy. And basically one of the interesting examples, you can calculate how much power is radiated by sun, our sun. So that's what we can do as the last example. If temperature, let's say about 6,000 Kelvin, the radius of the sun, I know that it's about 109 times greater compared to the radius of Earth. So it can help you to calculate the area of the sun. Find the power radiated. By this star. We're talking about something like a star. We know the temperature at the surface, and we know the radius. So then the question would be, if you have this radiation coming out as a black body radiation, then what will be the power? And I will definitely need your help because it's not easy for me to calculate it, but let's see. So in this equation, A is the area, sigma is, was it like 5, 6, 7, 10 to minus 8 watt meter square Kelvin power 4, and T is the temperature. Yeah. So you have a very hot object, 6,000 Kelvin, and the area is huge. The surface area of our sun is the radius of the sun is 100 times greater than the radius of Earth. Then the question would be, if I apply Boltzmann law, Stefan Bosman Law, can we estimate the power radiated by this object? And of course we can, yeah, it's not the question. Just for fun, let's estimate, compare the power to 1 kilowatt, how many watts, how many joules emitted by every second by our sun. Okay, let's do this. Power, area, constant, temperature, power 4. Area. For area, I need radius. Let's change it to meters. So help me. 109 Earth radii. What is the Earth's radius?
It's basically 700,000 kilometers. It's a bit less than that.
370 or something like this, kilometers, yeah? Let me say some 1, 2, 3, 4, 5. These are 5 digits here. Plus kilometers to meters, plus 3. 10 to power 8. Am I wrong? 1, 2, 3, 6, 7, 8. So I would say 10 to power 8 meters. Am I wrong? And then 1.09 multiplied by 637.
No, I mean the total, right? The total.
What do you mean the total? The radius, yes?
Yeah.
What is the coefficient in front?
I got 6.943. So
7, yeah, roughly.
7, yeah.
So then the area. How would you calculate area of the surface for the sun?
4 pi r squared.
4 pi r squared. We're not talking about disk. We are talking about spherical shell. So then we are ready. The area is going to be 4 pi 7 10 to power 8 meters, and I'm going to keep units now, square. This is the area, and you will get 10 to power almost 18, yeah, 18 meters square. Then the coefficient sigma, 5, 6, 7, 10 to minus 8 watt per meter square per Kelvin power 4. This is the Stefan Boltzmann constant, and finally, you have the surface temperature of 6,000 Kelvin, but you put it in power 4.
So the final answer I got is 4.5 times 10 power 26 watt. Yeah.
I believe the more accurate answer is like 3.6 or something, but very close. And this is correct, 10 to power 26. Can someone confirm 4.5? This is enormous power, yes, 10 to power 26 watt. So this means the sun radiates 10 to power 26 joules of energy every second. And this is only electromagnetic radiation, only light. In all frequencies, we need to say. But because of the temperature, we can estimate F max, KT over H. If you plug temperature 6000 Kelvin, I should say your temperature should be close to yellow or reddish and yellow color. So at this temperature, the maximum radiation will be around yellow color, and this would be the total amount of power radiated by our sun. What about yourself, your body, human body? How much energy you lose or radiate as, so then F max would be roughly 10 to power 14 or 15. Oh, yeah. So maybe 14 and something. Yeah. What about human body? Human body. Let's take temperature 300 Kelvin, maybe 310, doesn't matter. The area, I don't know, what is the area of human body, of the surface, roughly? 1 meter square is too much, yes?
You can consider a cylinder, right? A cylinder.
Yes, cylinder. 2 meters high, I don't know, 20 centimeters radius. Circumference 2 pi radius multiplied by length. 6, 0.4. Oh, no, it's not bad, it's not that small. So I would say 0.5 meters square would be not bad estimation, yeah? Or, well, no, what I'm talking about.
And the temperature is rather 310, right?
Yeah, but this is estimation, yeah? So this is 3 or 2, 3 meters square. Okay, roughly, it's a very rough estimation. The surface area of human body is, let's say, 3 meters square. The temperature roughly 300 Kelvin.
Yeah, because it's a fourth power, it will affect.
Yeah, oh, you mean this 10?
Yeah.
Okay, 310. Then how much power we gonna emit? Three meters square is the area. The Stefan Boltzmann constant, yeah?
Mhm.
Watt per meter square per Kelvin power 4. And then the temperature, power 4. So we're gonna get a not small number, yeah?
It's 1570.
Did you say 1570?
If I'm not wrong, yeah,
No,
1570.
I don't know. One,
Yes.
1570.
one
No,
point 1.6, and then
10 to the 3.
10 to power 3.
No, it's 1570.9.
Yeah, exactly. Yeah.
1000, and then you say
57.
5.
570.9.
Okay, 1. So it's a lot of power, yeah?
Yeah.
1.6 kilowatt.
15.
So how can you understand it? Why don't we feel this? If I would lose energy at this rate, I can work as a microwave for a while. Why I don't feel this loss of energy?
What do you want to feel?
I mean, you're losing this energy, yes, because you radiate.
Well, but you are eating also, right?
Because ambient temperature, yes. So if you talk about human,
No, not.
there is ambient temperature.
Okay.
So you receive energy and you radiate it back. So you are in equilibrium with the environment. You don't feel this significantly. How can you feel it? Remove environment. Yeah. Put yourself in empty space. Empty space. In empty space, you're gonna radiate only. So you're gonna cool down pretty fast.
Well, still there is a certain difference, right? Because, for example, what temperature we have now, like 20 degrees Celsius?
Yeah.
Yeah.
Oh, but it's gonna be a very small difference. Yeah. Yeah, I agree. So you mean my ambient temperature is lower than my body temperature?
Yeah, let's say like 290 Kelvin.
Mm-hmm.
The area is the same one because it's the area
Yeah.
of contact. Yeah.
I agree. So then you can compare, yeah. So how much power you receive? Let's say you say 300 compared to how much power you radiate back because you are hotter. So then you can estimate this coefficient.
Yeah.
So my goal was actually to play around today with this equation with Stefan Boltzmann Law, and I believe these couple examples are the best. And then the first part is to play around with the energy of one single photon and how you can calculate the wavelengths and the frequency and things like this. So basically this is a great equation to remember. We talk a little bit about radiation of light from hydrogen. So at least you learn something about H alpha line and the wavelengths for H alpha line. So Amaro insists that this should be 3 here. For astronomy, it's a very important line.
Mhm.
So then, if I can use another 20 minutes to talk a little bit about Compton Scattering, and we can finish for today. So if you want more examples, we can just do more examples. I don't know how you're enthusiastic about, because when you solve examples, actually, this is when you start to understand what's going on. Oh, by the way, just to finish this question, the typical frequency which we're gonna emit would be our temperature over Planck constant. And if you compare to 300 Kelvin versus 6,000 Kelvin, this is the sun, yeah? And the typical frequency corresponds to visible light, yellow color. What can you say about our frequency when human body?
Yeah, it's infrared.
The frequency is lower by what factor?
20 times.
You have human, you have sun. The only difference is the temperature, yes? It will be 1 over 20. So then the wavelengths we emit will be 20 times longer than emitted by the sun. So wavelengths human over wavelengths from sun, 20. If typical wavelengths for the sun is about yellow color, I don't know, let's say 500 nanometers. So if lambda sun, I'm gonna take like a middle point, 500 nanometers. Then what we gonna emit as human would be 20 times longer. So it will be 10,000, yeah? This would be infrared radiation. So we have non-zero temperature. We do radiate light, electromagnetic radiation. But the peak frequency is low because our temperature is low, and the typical wavelengths corresponds to infrared radiation. It's different, for example, for hot objects like the sun. For the sun, the temperature is too high, so the frequency is high, wavelength is significantly shorter, so it's a visible light. But for human, so we can see this wavelengths and this radiation, but we can make a device which can see this radiation, yeah? Like a night vision device.
Mosquitoes see it.
What?
Mosquitoes.
Mosquitoes?
Mosquitoes, yeah.
What about mosquitoes?
They see infrared.
No way.
Yeah, that's why they get you in the dark room.
I don't believe so.
Yeah, yeah.
Mosquitoes can see infrared radiation?
Yeah.
You're joking away.
And bees ultraviolet. Bees, they see ultraviolet. So the pattern that they see in a flower is different than what you see. It's not exactly when you see a flower, you see different colors and a certain shape.
Can you send me an article so I can forward to everyone?
The bees see it differently. They don't see exactly the same pattern of colors. They see something different.
This is fascinating. I did not know that mosquito can see.
Snakes can detect also infrared. They have a sensor in the, apart from the eyes, they have at least some of them. Apart from their eyes, they have a sensor of infrared radiation. They can catch their prey at night.
I did not know this. I thought mosquito can smell you.
Maybe.
Oh, I don't know. But it's interesting to investigate further. If you have an article where it's written, I would appreciate if you forward it so I can forward it to entire group. That would be fun. So at this point, I want to finish examples. I want to talk very quick about Compton Scattering, but just at the level of idea. And mainly I want to just introduce the photons, finally. When people talk about Compton scattering, you mean something like this. You have a stationary target like electron, you have a pretty high energy light, maybe X-ray, and then you have scattering. So because of the interaction, electron will go one way and light will get scattered. So if this was the gamma initial light, then you have a gamma prime scattered light, X-ray radiation, and you have recoil electrons. Yeah? Electron. What's so interesting about Compton scattering? From classical point of view, if you have electromagnetic wave and you have a particle inside electromagnetic wave, the particle will start to oscillate at the same frequency as this light. So when electron will start to oscillate, it can emit another light, but this scattered light should be of the same frequency and the same wavelengths. Because the electron was oscillating on the same frequency as the frequency of incoming light, electromagnetic wave. So I believe people introduced this angle theta. So what we notice on experiment, that the wavelength of scattered light is less than the wavelength of initial light, some constant, and 1 minus cos theta. So cos theta is the angle of scattering. So depending at which direction light is scattered, you're going to have different the wavelengths of scattered light. And I can relatively easy to change it to maybe frequency as well. So if I, but I don't want to do this, yeah? So maybe something like this, 1 over lambda minus 1 over lambda prime would be lambda c lambda prime. And if I multiply it by speed of light, then it's going to be frequency, shift in frequency. So f prime, correct me if I'm wrong, lambda c over speed of light, 1 minus cos theta. It doesn't really matter. What does matter is that there is a shift in frequency, and it was hard to explain. Why do you have shift in frequency? Why do you have a frequency of scattered light always less, and the wavelength of scattered light is always longer? And this was experiment, yeah? So we would try to explain this experiment from classical point of view, which is hard to explain because I would suggest that you should have practically the same frequency and the same wavelengths for the scattered light. And we can try to explain this from photon point of view. What if you don't have like electromagnetic wave, but you have this E gamma, like a photon? And then you have an electron, so you have basically head-on collision of two particles. But during the collision, you have energy conservation law, yes? So let's say electron will go one way, electron will acquire some energy. So the light will scatter it. It will go other way. Then the energy of scattered light should be less. So if I try to write energy conservation law, this is the energy of my initial light plus stationary electron. Then electron will acquire some energy. Then there is no problem to explain that the energy of scattered light should be less than initial energy, because you simply have energy conservation law. Now, if I remember that energy is related to frequency, I can get the shift in frequency. So this is energy of recoiled electron, and this is a change in frequency, and this is a Planck constant. Yeah? Again, if I look at the picture as interaction of my photon with electron, then the change in frequency or change in wavelengths, it's pretty natural. When photon gets scattered, part of its energy will be transferred to the electron. So the energy of a photon should decrease. What can be more natural than this? But when energy is decreasing, that means the frequency should decrease. So then I can try to explain this phenomenon, the Compton scattering, by doing this. But this is not enough. We have to also explain the dependence on the angle.
Can you assign a momentum?
We have to assign the momentum. And this is where it becomes really, really interesting. So let me write it again. So E gamma will go to recoil energy of electron plus scattered photon, yeah? Plus, you have initial momentum associated with the photon. And initial momentum is a vector. And this is where direction will be important. And this is initial momentum should be equal the final momentum of my system. So you can rewrite it like this. P gamma minus P gamma prime equal P electron. And then you can make this square. Double dot product. So I don't really want to go into details because that will be too much for me. But you can see from this equation that this is where cos theta can come and again. Yep. So if you very carefully analyze the Compton scattering, and if you really want to get the correct description of Compton scattering, the conclusion, and let me just jump to the conclusion, because I want to switch to real quantum mechanics from next time. Conclusion, and now I want to just finalize the answer. We have to assign momentum, so photons. They have energy, but we also have to assign momentum, and finally we can think about what is the mass of the photon. So energy, momentum, and finally mass. These are three ingredients which you need for a particle. And the Compton scattering actually puts some final accord in all this game. So when Max Planck started, we introduced just a gamma. Then photoelectric effect, you need a gamma to explain photoelectric effect. In this case, you don't care about the momentum and the mass of the photon. But when you study Compton scattering, and you would like to get the correct dependence on the scattering angle, then you have to talk about energy and momentum conservation, and you have to introduce momentum and the mass of the photon. And when you do this, you finally say that my photon is a particle of light. And this particle has energy, and this particle has momentum, and this you have like a normal momentum conservation law for interaction between photons and other particles. And this particle has mass. Of course, it would be nice if I can derive it to you, because I just need to analyze these equations. It is not that hard actually, but still, it's gonna take me a while if I would like to analyze it. I would probably say you have to take E gamma minus E gamma prime equal E gamma, E electron, make it square and take the difference. And in this case, you can get something close to experimental value. But I would just formulate the answer, and then we will finish for today. So the answer is the following. E gamma is related to frequency with the coefficient of proportionality, the Planck constant. P gamma as a vector is related to wave vector, K. But I'm gonna start with just magnitude of this. And as a magnitude, I would use the same Planck constant over the wavelengths. In reality, if I have to look at this as a vector, then lambda has no direction. What has direction is a wave vector. So I'm gonna multiply it by 2 pi and divide it by 2 pi. And 2 pi over lambda I replace with vector k. What I have left is h over 2 pi. So this would be another way to write down the momentum for the photon. And this is where for the first time h bar appears. H bar is simply Planck constant over 2 pi. It's a very convenient combination because it can relate your momentum and the wave vector. And something like 0.55, 10 to minus 34 joules per second. It's the same Planck constant. But what is more interesting, how the momentum and energy are related to each other. Can someone confirm that the frequency multiplied by lambda is the speed of light? Yeah? Or no? Or yes? Do you know such equation? Physics 2 people.
Yes.
Okay, frequency multiplied by wavelength is the speed of light. What kind of relationship you would assume between E gamma and P gamma? Let me take a ratio between them. E gamma over P gamma. E gamma over P gamma.
Let's see.
Sorry, I couldn't hear. What did you say?
Lambda F.
H bar goes, Planck constant goes away. And what I'm gonna get is
Lambda F.
lambda F or
C.
C. This is very interesting because we get something like E gamma equal P gamma multiplied by speed of light, or E gamma over P gamma is C. This is strange. What is the normal relation between energy and momentum? Normally, we would say energy equal mv squared over 2. Or we can say m squared v squared over 2m. I'm going to just multiply by m and divide by m.
P squared over 2.
P squared over 2m. But, so when my kinetic energy is proportional to p squared, this is something you would normally guess for a particle. And this would be a way to introduce the inertia, the mass. But look at this. What does it mean? To get a complete answer to this, we should look at the particle as a relativistic particle. So this was for non-relativistic. For relativistic particles, the energy equals square root p square c square plus m square c power 4. This is one of the famous Einstein equations when you can relate energy to momentum. This is the momentum of the particle, this is the mass of the particle, this is E energy. If you have a slow motion, for slow motion, this energy would be equal to the rest energy plus normal kinetic energy, like this. The rest energy people usually don't consider, and this is what you have p squared over 2m. You can just make expansion of this square root. It's something called Taylor expansion, but we're not going to do this. Can you compare these two guys? What can you tell about the mass of the photon? If my energy of photon is described by relativistic equation, and remember photons are moving at speed of light, you should consider them as relativistic particles. Just compare, what should be m if you want to have this relationship? It's an avoidable conclusion.
Yeah.
Mass of photon, m gamma, must be equal 0. So it makes this even more mysterious at the very end. So if you look back, we had this technical part for examples. When I tried to convince you that all these equations with Planck constant, they work. And you can work with them and you can estimate some practically important things like power radiated by our sun or by human body. But if you look from the very beginning of the first lecture, Max Planck idea about E gamma, Albert Einstein explanation of photoelectric effect, plus Compton Scattering, we finally arrived to a point where we introduce particles of light. These particles are very strange. They travel at speed of light, but we know that it's impossible to travel at speed of light because for any object with mass, the energy will be infinite. But light has no mass, so it can travel at speed of light. So it has energy, it has momentum, it travels at speed of light, and it has no mass. And we have these experimental evidences, very, very solid experimental evidences. Okay, it's again longer than I expected, but I hope you enjoyed this. And then next week we don't have a meeting because of the spring break. So next week we will continue already talking about quantum mechanics for particles, not for light, but it all started from light. So now we can just talk. If you have questions, comments, was it clear?
Professor, perhaps now that you just completed Compton Scattering, you should mention that how, remember the question that I asked, why does the sun emit a continuous spectrum when it's mostly made out of hydrogen, and hydrogen emits in these very particular wavelengths, and it's either ultraviolet or infrared, and there's only one visible, so it should be red color. And you
Yeah.
said it's because of scattering.
Yeah. So apparently the scattering, the chance to get scattered has some probability, and probability usually is not very large. So most likely the light will go through this, especially if you have a neutral atoms. So the light will go through these neutral atoms without serious problems. But what becomes important is the density of your medium. And this probably Amaro can comment on this if Amaro has something to say. Let's say you have air. So you have a low density. So then you have a high light generated by emission. So and the light pretty much will go through this low density, yeah? Density gas. What Peter is talking about, that when light is emitted at the center of our sun, at the star, somewhere where it's very hot, light is emitted. So sun centers. Then the density actually of the environment, of next layer of the sun, it's huge. So the light emitted cannot go through without scattering. So, and you may expect that light will just change direction once or twice, because probability to get scattering is not very large. But in reality, because the density is so high, the light is get completely confined in these layers. So eventually, of course, it will go out from the sun. And this is what we detect at some point. And during this scattering process, of course, the frequency will shift, because every time you scatter, you change frequency a little bit. If you have many scatterings, then your frequency can be almost any. So that's why you can have a continuous spectrum. But, Amaro, how long does it take for light to go through the sun?
Millions of years.
Millions of years.
Yeah, and then it takes 8 minutes to go to Earth.
And then it takes 8 minutes to go to us. Can you imagine this?
So we are looking at a very old light, right?
Well,
Wait, I'm sorry, can you repeat that?
yeah, sure, with my pleasure. So this means, let me draw a nicer picture for you. So you have a star, yes? So the star has core where nuclear reactions are going on. So it's very hot and very dense.
Sorry for interruption. Indeed, it's gamma rays, right? Because
Yeah, gamma rays, because
yeah.
the energy, the temperature is very high. But then you have next layers. And I don't remember, one is convection layer, one is radiation layer. When you transfer energy through radiation.
For the sun, the first one is
radiation, yeah?
Radiation, and
then you have a convection layer, when basically you have a gas moving around. So you can transfer energy to surface by convection. It's like you have something boiling and the water is going like up and down, like hot gas is going up, cool down and goes down. And then you have maybe some surface, like a chromosphere. And this is basically our sun, yeah? So now, normally for light to travel this distance, it should take definitely less than 1 second. We can estimate it, yeah? The The radius was, if I remember correct, 10 to the power 8 meters. Yeah. If you divide it by speed of light, so we are talking about something less than a second. For light emitted somewhere here to reach the surface of the sun, it should take less than 1 second. But it takes millions of years for light to reach from the core to the surface. Not 1 second, millions of years. This is a statement, Elizabeth. The statement is that the light cannot go through this layer, radiation layer, freely, without any problem.
Because of the density?
Yeah, because of scattering process. Because this is very dense, and then when light is trying to get through, it's actually changed direction. So it gets scattered. And then it gets scattering again and again and again and again. So the path is getting very complicated. So eventually, of course, it will go out. But it will take a while. Now, Peter's question was, why do we see continuous spectrum? Because if hydrogen emits some radiation because of this excitation and relaxation, then it should be the same energy we just talked about, like H alpha lines and all of this. There should be emission line spectrum. Only certain wavelengths should be emitted. But during this scattering, the light can change frequency. And it can change its frequency to basically any frequency. With time, you can get all the frequencies possible. So when this light comes out, you have what's called continuous spectrum. So there are two questions were discussed. One is the time, and the second is why do we have continuous spectrum? Thank you, Omar and Elizabeth and Peter.
Thank you.
Yeah, are we good for today?
Yeah, still, I think I have to think a bit more about this, but I'm thinking now, right? Because this, apart from the lines, the absorption line that you have in the photosphere of the sun, which are darker than the background spectrum.
Yeah.
If you don't take into account the lines, you have a black body radiation. So the profile of the radiation is like a black body. But okay, so how can we make this compatible with the scattering, right? Because okay, it seems that we have all these different radiations, different wavelengths because of the scattering. But that will give us a certain profile that doesn't have to be necessarily a blank curve, like a black body radiation. I don't know if I'm clear what I'm saying. So we're having a spectrum like it is a cavity, a resonant cavity.
No, Amaro. So once you have a light in equilibrium, basically it's light in equilibrium. There would be certain distribution, Planck distribution, which corresponds to certain temperature. Yes. So when light slowly migrates towards surface, the temperature low downs, yeah? And you just change temperature, you slightly change the distribution. This is not a very fast process, yes? It takes time to move to the surface. So when temperature drops, I'm not sure that I understand your question right.
No, my question is if this, sorry, I don't want to interrupt you. My question is you have okay, suppose that you have a black body profile originally.
At certain temperature.
When you are in equilibrium, right?
Yeah.
But then you have this scattering. So it seems that this scattering is not affecting the Planck
No,
profile.
no. When we speak about black body radiation, we assume that there is scattering. Because we assume that energy is distributed somehow equally between light. That it basically is assumed. It's like if you have a gas and particles inside the gas interact between themselves. And when they interact, they exchange energies. But this is called thermalization. This is perfectly fine. So, if I can...
Okay, I understand a bit, but not completely. But I have to study more. What I'm trying to say is this. Suppose that you have a void cavity, right? You have a piece of metal with just a cavity inside. Like a hole, a hole inside a metal or something.
So let me first say something. Let's say you mix cold gas and hot gas. So they may correspond to different temperatures. But because of the collision, they will redistribute energy. And the distribution will equalize. And then you have a one system at given temperature. So the process when you go from some system to equilibrium is called thermalization. So, and this thermalization happens because of the interaction. So there is nothing wrong for photons to be scattered. It will just help the thermalization process, yeah. The scattering and the interaction doesn't contradict or violate Planck distribution. In opposite, it helps to reach equilibrium. Because Planck distribution describes system in equilibrium. And how you reach equilibrium? Due to interactions. You have something very fast and something very slow. They collide, and after collision, they have equal energies. This is thermalization. This is what you actually want to have. No?
Yes.
I didn't convince you, I guess. Okay, thank you so much.